Hey guys, today we're going to be talking about designing Butterworth filters in digital signal processing. This is one of the most essential topics in digital signal processing, Butterworth filters. So let's get cracking. So what are we looking for when we talk about designing a Butterworth filter? What exactly is designing a Butterworth filter or designing any filter for that matter? So we have learnt about transfer functions, right? Transfer functions of a system and signals and systems and control systems, multiple such subjects, many such topics, which is h of s, right? This h of s is given as y of s by x of s, right? For those of you who don't know, for the uninitiated, y of s is the output of the system given in the s domain, and x of s is the input of the system in s domain, and the dividing this value gives us something we call the transfer function, that is h of s. So in a Butterworth filter's perspective, even a filter has a transfer function. Once we find this h of s, we consider the filter to be designed successfully, right? So the designing process. I'm going to explain the designing process in steps. Step 1, we need to find the order of a filter. This order is denoted by this capital letter n. Now n is given mathematically as n greater than or equal to log of root over 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 divided by log of alpha s by sorry divided by log of omega s divided by omega p. Now I know this looks complex, right? It's a pretty huge equation. It's pretty huge inequality. We have alpha s, we have alpha p, omega s, omega p, so many variables. We have log. Scary, right? Absolutely not. I'll tell you why. Because we know each and everything that is given to us in this particular inequality. Alpha s is our stop band attenuation. Alpha p is the passband attenuation. Omega p is the passband frequency. Omega s is the stop band frequency. Still unclear? Relax. These values will be given to you 99% of the time. Any problem in the basis of designing a Butterworth filter will be given to you. Unless, of course, we are going to be dealing with derivations, we will have to deal with variables as a whole. But if you're going to be designing a filter, these values will be given to us in some or the other form. Now that we have n, what do we do with it? N will usually come to us in any decimal format. It can be 1.23, 2.34, of the sorts. So what do we do with this? Because we need an integer, right? If n, I will take an example to make things simple. If n is greater than or equal to 2.25, we just take n to be 3. So the order becomes 3. If n is say greater than or equal to 3.565, we take n to be 4. It's as simple as that. Now this is something I like to call the high table. I call it that. That's not the official word. Please don't come at me. This maps the order of a filter to the denominator of the transfer function. To the uninitiated, a transfer function h of s is usually of a form numerator by some denominator. Alright? Please pardon my handwriting. I'm writing using a mouse. I do not have a touch pen of sorts. So coming back, say n is equal to 1. So the denominator of the transfer function will be s plus 1, and so on and so forth. This table forms one of the baseline of designing a Butterworth filter, so it's good to have in mind this denominator. Alright, this value this value right here takes place of the denominator. We know that any transfer function is given by h of s. This table gives us the denominator to that very h of s. Next, we have something we call the cutoff frequency, omega c. Omega c is given by two formulae. One in terms of, let me change my color, one in terms of omega p, one in terms of omega s, which is our pass band frequency and our stop band frequency. We can use any one we deem fit, whichever is more convenient to us. So omega c is given by omega p by 10 power 0.1 alpha p minus 1 to the power 1 by 2 n, or omega c is given by omega s divided by 10 power 0.1 alpha s minus 1 to the power 1 by 2 n. We take this omega c value once we have it, and we substitute it in the format s is s by omega c in our transfer function h of s. Simple, right? Still confused, right? I know that. Most of you all are going to be like, that entire thing went over my head. Some of you all are going to have understood 1/4 of the thing, half of the thing. Nothing to worry, because there's nothing in this world that cannot be fixed with a small little example. So that's what I'm going to do. Let's take this example. Design an analog Butterworth filter with 2 dB passband attenuation at a frequency 20 radians per second and at least 10 decibel stopband attenuation at 30 radians per second. What do we know? What have we learned? From Steve Jobs? Oh, I heard this from Google one. Design an analog Butterworth filter with 2 dB passband attenuation. 2 dB passband attenuation. Passband attenuation makes this alpha p. At the frequency 20 radians per second, we have our omega p, at least 10 decibel stop band attenuation. We have our alpha s. At 30 radians per second, we have our omega s. It's as simple as that. We take all these values and we put it right here in this equation in our quest to find n. And voila, we have n right here. We let these calculations to be done by a scientific calculator. No effort taken. 2 snaps, and we have our n with us as 3.37. Step 2 would be to round off n to the next greatest integer. That would make n is equal to 4. Therefore, the order of this filter is 4. Remember the high table? The one we had met in our previous slide? He's back. And we need his help. This bad boy's help right here to solve this problem. We found our n to be 4. Right? What is n is equal to 4 map to? Maps to this bad boy here. So we take this bad boy and we put it here. We consider the numerator to be 1, and this is our transfer function h of s. Then we let our transfer function sit there for a bit while we try to find what the numerator is going to be, or what the other half of the transfer function is going to be. Anyhow, any way you want to look at it, we try to find the cutoff frequency, which is given to us by omega c. Omega c, I'm going to be using the omega p formula. You can use the other one, it's your choice. Omega c is given by omega p divided by 10 power 0.1 alpha p minus 1 to the power 1 by 2 n. Plug this value here, plug these values here, and therefore we get our omega c value to be 21.3868. Coming to the very final step of the problem, we take this value here and we put it as s, given by s by 21.3868, because if you remember, we were supposed to take s by omega c, right? We were supposed to substitute s as s by omega c, so we know our omega c value to be 21.3868. So we snap it back in place and we substitute it in our transfer function. Once we do that, we get this big boy right here. Nothing to worry about. Some basic algebraic, we use basic algebra to solve this. are pretty much our scientific calculators can do more than half of the job for us. Ta-da! Here we have our transfer function. H of s is equal to 0.20921 into 10 power 6 divided by s squared plus 16.3686 s plus 457.394 multiplied by s squared plus 39.5176 s plus 457.394. This is quite a mouthful, but let's face it, most of the calculations are not done by us, so nothing that bothers us, right? So this is how we design a Butterworth filter in digital signal processing. This is one of the most essential topics in digital signal processing. It forms the fundamental, and once we learn Butterworth filters, we can go ahead and learn many other types of filters, designing them, such as Chebyshev filters, finding the poles of a Butterworth filters, many more topics to come. But this is extremely essential and almost a sure shot question for electronics engineers or electrical engineers. I hope I could be of some help to you. Hope this topic is clear to you now. Thanks for watching. Please like, share, and subscribe to Mass Tutor YouTube.